Alrighty, hello and welcome to topic 3.8, exponential growth and decay. So, I think this topic is primarily covered in Algebra 2, or at least in most high schools. However, what we're going to be doing in today's video is really looking at it through a calculus perspective. Now, you might be amazed that in math, there's several different ways of looking at something. You could look at a function to solve it. You may want to know how it behaves. You may want to know a maximum, a minimum. You may want to know when it's a certain value. You might want to find a zero. But in today's video, we're looking at this through a calculus perspective on exponential growth and decay, which we've already seen the exponential functions. So, just to start out, or just as a reminder, in the last second to last video we made, we went over a lot of natural phenomena. And a really cool thing about natural phenomena, interest, a lot of things in physics too, all of them, all of their growth and decay are proportional to their size. For example, if we have, and this is just a calculus way of saying this, or a math way, if we have a function y is equal to k times by f of t, y is equal to k f of t, then if we find this derivative of this function, what we'll see is that we are going to get this f prime of t, this y prime of t is equal to k, which is some proportion of growth, times by f of t. Which is really cool. So, where will we really see this at? Or I suppose a more general way of saying this is the derivative of y with respect to t is equal to k times by y. So the derivative of the function y is equal to a constant times by the function, by the original function. Alright. And we actually have a name for this in math. This is called the law of natural growth. Natural growth / decay. Alright. Now, you may recall that we actually have a very specific function, or a group of functions, but we're going to say one specific function here, that follows this condition to a t. And later on, once we get to integrals, whatever those are, I don't know. Just kidding, I do. But once we get to integrals, I will show us why this works and why the function is the function that we choose. So, let's see. If we take a derivative, or let's say that we have a function y. Alright, let's call this y. Y of t is equal to c times by e to the k t. Alright. Now what I want to do with this is we're going to take the derivative of this with respect to t. So we get our y prime, or a derivative of y with respect to t, as shown up there, is equal to, well, to start out, we have the derivative of the constant, which we can bring out front, so it's just c, times by the function, which is going to be e to the kt, times by the derivative of the inside function. Well, the derivative of k times by t, that's just a line, so that's just going to be k. Now, interestingly enough, we have a name for this already. This right here is just equal to y, so we get dy dt is equal to y times by k. So now you can kind of see like where we get this law of natural growth from. And why the only solution to this differential equation, which is what this is called because it's an equation given, or it's a derivative that's a given, not an original function. The only solution to dy dt is equal to k times by y are the functions y of t is equal to y naught times by e to the kt. And that's it. So I suppose we want to look at a bit more of a specific example. I'm going to clear off my board just a small bit. Alright, there we go. Alrighty, so the next thing I'd like to talk about is population growth. Alright. So, population growth is one of those like natural sciences. It's in biology, in fact. So you may recall that populations will often grow exponentially. They're definitely not linear, but they're definitely proportional to their own size. For example, I did a colony of bacteria problem in the natural sciences episode. The colony of bacteria is going to be growing at a rate that's proportional to the amount of bacteria. Kind of makes sense. If you have 1 bacteria, then it's going to be growing slower than 5 bacteria. Right? I think so. Alright. So, before we continue on with this idea of population growth, I just want to take a moment to talk about the K. What does this K truly represent? Why does the K matter? Well, this K, and we're going to just write this out, we know that our derivative of population, and this can go for anything here with respect to time, is K times by the population. Okay. Well, if we want to know what K is, we can just solve for K. So K is really just the derivative of population with respect to time divided by population. But it gives us an easier way of saying the growth rate's proportional to the population size. Instead, you can say the growth rate is constant, because that is true. It is growing at a constant rate, which in this case, or in the case that I'm about to show you, is in percent. if we are given the function P of t is equal to P naught times by e to the 0.02 t, and we want to know its growth rate, well, P prime of t is going to be equal to P naught times by 0.02 times by e to the 0.02 t, which is really just p. So we get P prime of t is equal to 0.02 P of t. And we can see very clearly that this value, 0.02, is our k. So we can say it's growing its relative growth rate is 0.02. All right. Well, I feel like we're now ready for a little practice here. So, example. Use the fact the world population was 256 million in 1950 and 2,560 million in 1950 and 3,040 million in 1960. Assume growth rate is proportional to population size. What is the relative growth rate? And predict the population in 1993 and 2025. All right. So, to start out, we know P of t must be equal to some P of 0 times by e to a constant times by a t. We don't know what that constant is just yet. We know that P of 10, which I suppose is what we're using here. Yeah, that's what we're going to use here. And we know this P naught is actually going to be 2,560. All right. And we know that P of 10 is equal to 3,040. But we also know that must be equal to 256 times by e to some constant k. And we know this is 10 years later, so its time is 10. Now what we want to do is we want to solve for this e to the k 10, or e to the k times by 10, and we get 3,040 divided by 250, or 2,060, which I guess we can simplify to 304 over 256. All right. Then what we can do is we're going to take the natural log of both sides. Sorry, this is kind of strange notation, but I use it a lot. So we get k times by 10 is really just the natural log of 304 over 256. Now to find our k, all we have to do is divide both sides by 10. So we get the natural log of 304 over 256 divided by 10, and that's our k. Plug into our calculator, and we get an answer of 0.017185, and a few more decimals, depending on how many decimals your calculator does, but I'm guessing that's probably infinitely repeating, but I digress. Alright, so now what do we do once we found this constant? Well, we can now find our original formula. And this is more of like an Algebra 2 topic, I'd like to say. It's not really calculus. the only calculus part of this is, instead of telling us it's an exponential growth rate, it's telling us its growth rate is proportional to its population size. So I think, in general, this is going to be relatively easy to wrap your heads around. So P of t in this case is going to be equal to 200, or 2,560, times by E, and I'm just going to summarize this to 0.02, why not? 0.02, makes our math easy, times by t. Now, if we want to estimate in 1993 and 2025, all we have to do is do 1993 minus 1950, and we get an answer of 43. So P of 43 is going to be 2560 times by e to the 0.02 times by 43. And what we get is the population estimated in 1993 is 5,359 million. Alright, and then in 2025, which is the year we are in right now, as of like a few days ago, kind of still shocked about it. 2024 went right by quickly, for me at least. 2025 minus 1950. That would be 75 years, right? Yeah, 75. Alright. So now I just have to plug in P of 75, which is 250 or 2,560 times by E to the 0.2 times by the 75. And for our answer, we get 9,200,000, or sorry, not 9 million, but 289 plus some change, but I'm not going to worry about the change. Alright. And to actually compare those numbers to the world populations at the time, the world population in 1999 was actually 5,557, or yeah, 5,500,000,000 something. But you can see these estimates are actually really close to each other, surprisingly enough. And if I really wanted to, yeah, there we go. Now they're the exact same, like, format. Alright, and then, like, if we're comparing 2025, now, of course, it's going to be a bit worse of an estimate because we're a bit farther away, but the population in 2025 as of right now is 8 billion. Yeah, about 8.2 billion. So it's a bit of an overestimate, but it was still really close. The thing that I find surprising is that it went from an underestimate to an overestimate. But I'm pretty sure that was just because of pandemic and some other world issues at the time. Radioactive decay. So the one thing that we haven't talked about so much yet is what happens if our K is negative. So, of course, it uses the same example. So we have the dm over dt, and let's say that the m is just mass, is equal to k times by m. It looks the exact same, but in the case of decay, this k needs to be a negative number. Doesn't matter what negative number, that's it. It just needs to be negative. Other than that, it's the exact same as what we've already been doing. So we want to find the half-life of radium if the half-life of radium is 226, or of radium 226 is 1,590 years. So we want to find a formula for the mass of radium if it has 100 milligrams. So to start out, we are going to say that we have 50 is equal to 100. I suppose I should change my color for this. This makes it probably has been making it hard to see, but I have a 50 is equal to 100 e to some kt. Alright. We actually know that this t that we're using is 1,590. So now what we need to do is we need to divide this 100 to the other side, if you follow, and we get 1/2. Now we need to take the natural log of both sides, and what that's going to get us is negative natural log of 2 is equal to 1,590 k. So k is just equal to negative natural log of 2 over 1,590. Then what we can do is we can just plug this into a formula. We know that I suppose the mass is a function of time is equal to 100 times by E, and let's actually compute that value of K. It is a very, very small number here. So if I'm doing this right, it's going to be equal to roughly about 0.0004. Sorry, I believe I accidentally added in one too many zeros, so there we go. Alright. Like 0.35. I'm going to keep this constant k up here just to make my life easy, but we have stated our k down there. Alright, now we want to find the mass remaining after 1,000 years. So now it's just m of 1,000 is equal to 100 e to the kt. Remember that this k is this like 0.00435. So what we get for our answer is 64.666 grams. Or sorry, milligrams, I believe this was supposed to be. Yep, milligrams. Alright, there we go. When will the mass be reduced to 30 milligrams? Well, this is just an algebra problem here. We have to solve 30 is equal to 100 times by e to the kt. Divide both sides by 100, so we get 3 over 10 is equal to e to the kt. Take the natural log of both sides. I'll just, there we go. Makes it easy. So we get the natural log of 3 over 10 is equal to kt. Remember, this k is an actual number we know, so we get the natural log of 3 over 10 divided by k is equal to t. Plug this into our calculator, and we will see that it will take 2,761 years for it to have a mass of 30 milligrams. Alright. Newton's law of cooling. Very cool. Ah, a nice little pun. Well, this is just another example of something being proportionate to its own growth rate. So, Newton's law of cooling states that the rate of cooling of an object is proportional to the temperature difference between the object and its surroundings, providing the difference is not too large. If we set T of T to be the temperature of the object at a time T, then T of S is the temperature of the surroundings. Then we can formulate Newton's law of cooling as a differential equation. So this actually goes to show that d of T over the derivative of T is equal to a constant times by the function T of T minus T of S, which is the surroundings. Okay. So, we can say y of T alright, so we are going to say y of T is equal to T of T minus T of S then we are going to take the derivative of this with respect to T. So we get y prime of T is just equal to T prime of T, because this T of S is just a constant, really. And because of this neat little fact right here, and now that we know that the derivative of y of T is equal to the derivative of T, we can say that y prime of T is equal to K, and this kind of deserves a drum roll, please. And we know that this T, this function of T minus T of S is Y. And surprisingly enough, we get another thing that's proportional to itself in growth. Alright. Cool, isn't it? Well, let's use our newfound power to find an answer to this problem. So, a bottle of iced tea at room temperature, 72 degrees Fahrenheit, is placed in a refrigerator, 44 degrees Fahrenheit. After half an hour, the tea is cooled to 61 degrees Fahrenheit. What is the temp of the tea after another half hour? And how long does the tea cool or take to cool to 50 degrees? So, to start out here, we know that the derivative of T with respect to T, or rather I should probably call this period, or no, temperature, is equal to K times by the temperature function minus the surroundings, which is 44 degrees. Alright. Then we are going to say that Y is equal to T minus 44. So then Y naught must be equal to T naught minus 44. Which we know T naught is 72. So Y naught must be equal to, this is 72, 28. Then you can take the derivative of y, as we kind of did up there, but we don't need to do that all again. So we know the derivative of y with respect to t is equal to k times by y, the constant proportion times by y. Alright, and we know our y naught is equal to 28. Alright, now let's get a function. So we have a y of t is equal to y naught, or not y naught, but y initial, which we know is 28, times by e to the kt. Next, we know that t of 30 is equal to 61. Alright, so t of 30 is equal to 61. Well, we need to get something in y's for us to use it. So y of 30 is equal to the 61, using our equation up here, minus 44. So we get 17. So now that we have this 17, we can now work towards solving this for the constant, because we know our 17 is equal to our 28 times by e to the k times by 30. Alright. Now we are going to divide both sides by 28. So we get 17 over 28 is equal to, if my pen wants to write, e to the k, or e to the 30k. Now we're going to take the natural log of both sides. So we get the natural log of 17 is really just equal to the 30k. Now the final step is we have to divide both sides by 30. So we get the natural log of 17 over 28 over 30 is equal to k. Punch this value into our calculator, and what we get is an answer of negative 0.016. Alright. Now we want to know, or now what we want to do is we want to use this to find the temperature in another half an hour. So, what we have to do is we're going to start out by saying that our y of 60 is equal to 28 times by e to the negative 0.016 t, or in this case 60. Plug that into our calculator. And we get an answer of 10.32, which I'm actually going to cut off that 32. But this isn't the temperature of the item. We know that temperature of time is given up here, but we don't have the temperature. So how do we get the temperature? Well, we know our temperature of any time x is going to be equal to y of x plus 44. So we know our temperature at time 60, or what we got from y, is 10. So 10 plus 44, and we get the answer of 54 degrees Fahrenheit after 1 hour. Finally, we want to know how long will it take for the tea to cool to 50 degrees. Well, I have to erase some stuff here, make some room. So to start out, we are going to plug in 50 degrees into our law of cooling. Ooh, did I just erase? I erased the equation that we were using. That's fine. There we go. We got it. Alright. So, we know that y of this time x so we want to know whenever this t of x is going to be equal to 50 degrees, which is whenever y of x is plus 44 is equal to 50, which means y of x needs to be equal to 6. Okay. So now what we're going to do is we're going to take the 6 and plug it into our equation and solve for time. Times by e to the negative 0.016 times by time. Alright, divide both sides by 8 to start out. So we get 3 over 14 is equal to e to the negative 0.016t. Take the natural log of the function. So we get the natural log of 3 over 14 is equal to negative 0.016t. Finally, divide that over to the 0.016t over to the other side, and we get the natural log of 3 over 14 divided by negative 0.016, and the time for it to get to 50 degrees is 96 minutes and 28 seconds, or like 98 minutes, 0.28. Alright, and that's our answer. Alright, well, I think that's all I'm going to have for you today. I hope you all enjoyed and found this video informative. I am sorry if this video sounded a bit more like, experimental in some ways, but also more chaotic almost. But this video is definitely not... It's something that I feel like is easier to explain with integral calculus, rather than having to take derivatives to show facts. But I digress. I hope you all have a wonderful rest of your day, and if you enjoyed, please like and subscribe, and I'll obviously be hopefully uploading more videos soon. Goodbye.